All right. Hello and welcome. Today we'll talk about processes and threads. And this part will be talking more. We will be talking more about processes, and the second part. If I have time, I'll upload another video on a thread. So just a way of review before we continue our discussion on processes. Just a way of the review what a process is. We talked about a process in the class. I explained how the CPU is program counter or instruction pointer would be reflected as you switch between one process and another, and that would not be free. We have to have processing overhead that the operating system, particularly the dispatcher or the scheduler, has to be involved to switch between one process and another. And another fundamental concept is the process context, which I will review, and we'll talk about process states and why we do context switching. And so for the second part, we'll cover threads. So just a way of review, I'm going to go over slides fairly quickly here. We say the process is an active entity, whereas a program is a passive entity. So an easy definition for that is that a process is a program in execution. A process is loaded into the memory and is ready for execution. Okay, talked about that, so I'm going to skip all of that stuff. Difference between an I/O bound process and CPU bound process. And this is a trace of processes. And this is very important illustration showing the processor itself. This is the CPU with CPU registers, where process would be running here, and at some point the process will be released when it is completed, or when a process encounter an error. So a process did like division by 0, it will be terminated. So that's another reason for termination. But while a process is running, it can be timed out because its CPU quantum has completed, and in that case it will go back to what's called ready queue. So this is the ready queue, which contains all the processes that are really qualified for running or ready for running. That's why we call it ready. But a process, while it's running here, it could initiate an I/O, like makes an I/O request from the disk, or wants a message from another process, or what does a fork system call. So there are certain system calls that be blocking. So there are blocking system calls and non-blocking system calls. So we'll talk about that later. But this is an important illustration. So suppose that you want like a message from another process, and so another process wants the same message. So these processes will be queued for the arrival of that particular message. So when that message arrives, then that event occurred, and then they'll go back to the ready queue to run again. This is similar illustration, and we said that this is the essence of the execution of a processes, which is built on the concept of multi-programming and time sharing. And in a way, this gives you the nice visualization that many things are happening at the same time, but in reality the CPU is executing one task at a time, one app at a time, one process at a time. But because of the time sharing, things look like, nicely executing in parallel. Talked about the scheduler and the dispatcher that these are responsible for switching the process from one state to another, from running a state to maybe a blocking state or ready state. Now, everything that we need to know about the process, its name, its state, who owns it, its ID, whether it has a parent process, what that parent process, we have to keep all the information about this process in what's called the process controller block. And that in reality, this process controller block contains the context of the process. So the process context describes the operational state of a process. Okay. So we comes so the process controller block, this PCB, has the operational state data, operational state information about the process. It got the main memory contents, where they start, the code segment, the data segment, the stack segment. Also, the CPU registers about the processes, the address and data registers, the program counter, stack pointer, the program status word or live flag in the Pentium architecture, and the segmentation registers. Well, these block where these the code segment are, where the data segment starts, and where the stack region starts. All these are stored in registers, and anything that the process is doing, like opening files, this process status and the process ID and the user action of that process, and so many other information that the process has. So this is sort of a PCB is a data structure that contains information about the context or the operational state of the process. The process could be running, could be waiting, could be ready to run. So that takes us to the process transition state, and these are the main state: the ready state, and the running state, and the waiting, or we call it also the blocking state. This is a timeout interrupt. So a process could be running, executing instruction at this time on the CPU, and then it would be its state would be running state. It could time out at some point, and then it becomes ready. Remember that illustration diagram of showing the queues. So it goes back to the ready queue. And we said this is a state. Okay, this is a transition. Okay, or the state of the transition, or the reason that you go from one state to another. So another state would be a new, and then gets admitted, goes right away to the ready queue, and then you can have a state terminate state, the process just finished execution or encountered a fault, and then it has to be terminated. But if a process can go from running state or waiting state or blocking state, if it initiates an IO, at some point that IO or event has completed, then it goes back to the ready queue or the ready state. So this is the reason of the transition from waiting to ready. Let's take this to another level. Look actually when a process is running, process is to be running in a user mode or a kernel mode, and that'll be described as user running or kernel running. So because a process is like handling a system call, or initiating a system call, it has to be handled by the kernel. That system call will be, of course, executed in a kernel mode, and therefore the process state will be a kernel running state. Another thing that here, if we zoom in, the ready state, this ready state, when a process is ready, it could be just normal ready, but there's another state that could be a process could be in a ready. I'm gonna abbreviate here, very hard to write with the mouse. In a ready suspended state. In a ready suspended state, a process can go from ready to ready suspended state if it's running out of memory. That's out of memory. This is the transition for it. So if we have like a limited memory, and then what happens is that we need to allocate more memory for other processes. What we need to do is to take some of these processes out of the memory and put them in the disk. So if a process is a ready state and we are encountering problems with the memory, problems meaning the memory is becoming less and less, then it makes sense to take that process out of the memory, so we can have more free memory, and this more free memory can be allocated to other processes. So out of memory, that takes you from the ready state to the suspended state. Okay, and once we a process can go from ready suspended to ready, okay, this way, if more memory becomes available. So like if these running processes in the system sort of like finished, then we will have more memory, and that way we can take that process from the ready state back I'm sorry, from the ready suspend to ready if we have not out of memory. Okay, so not OOM. Okay, so this is clear. Also, we could, if we're running in this situation out of memory state, we can swap out a process to the disk. Swap meaning taking that process from the memory and store it in the disk. So its memory locations are freed for other processes. So we can take a process that is waiting, and then do it like here, blocked, or W, okay, block suspend, okay, which is this state, and take it out from the memory and put it into the disk, and then so the transition for that will be similar to the ready state, so that will be out of memory. Okay, and the transition from state transition from waiting to waiting suspend or blocked, and this is another way, a block to block suspend will be not out of memory. Okay. Okay. So this is important. Of course, we've talked about in the class about going from ready to also running, and that will be, when the scheduler has determined its turn for that particular process that is sitting in the ready queue to run. So we call the scheduler and the dispatcher, and then actually we made a distinction between the scheduler and dispatcher. The scheduler is the one that has to do with the order, determines what the process has to run now, and the dispatcher is the one that would load the contents the contents, from, of course, the program counter block, for program controller block, the PCB, so it would load the CPU registers from the PCB that are stored in the PCB into the CPU registers, and that time the process becomes running. Okay. This is sort of like showing you how queues are implemented. The queues are implemented actually as a linked list. So actually, there's a difference between a queue and a list, and the implementation of the queues are just list. Okay, so what happens here? Just like you have a doubly linked list, or a single linked list like we have here. So we have here the PCB. So that this data structure, we said the program controller block, like the data structure are linked this way. Okay, so this is sort of like showing you how they are linked. So this is the head of the queue, and this is sort of like tail of the queue, and there are two processes on the queue as shown here, process number 7 and process number 2, and then these are the blocking queues. For example, this is a terminal, somebody waiting for like an input from the keyboard, and we have process 5 is waiting for that. And if you look here, here's one waiting for disk, and that the process that are waiting would be 3, 14, and 6. Of course, one thing to note here is that you see only one PCB found in any of these queues. So it doesn't make sense to see a process waiting like a process 5 waiting here, and then another process 5 waiting here. It doesn't make it. Just has to be it has to be only seen in one queue. Okay. Okay. Let's talk next about when we do context switching. When to context switch, and this idea has to do with going from execution of one process to another process. So in the concept of time sharing, we go from process 1 to process 2 to process 3, because the CPU quantum has completed. And multi-programming, we go from one process to another process because the process has initiated an I/O. So what happens is that typically hardware initiates interrupts. So when these interrupts they happen while the process is executing. In that case, we save the contents of the CPU state on the stack, and we go to perform the interrupt handler. And so the interrupt handler does its thing, and it may come back to the same point of interruption and continues, or that interrupt that occurred could be a system called blocking, or could be the end of the CPU quantum, a timer interrupt, which means we have to go and execute something else. So this bullet says it may no longer be appropriate to resume execution of the process, because that interrupt that occurred for different important reasons. That interrupt that occurred can indicate the completion of the CPU quantum. So it's a timer interrupt, and it says this 10 millisecond CPU quantum has finished for this process, and now it's time to go and run some other process. Or could be that that is a system call, and it's a blocking system call, meaning that system call has to initiate an IO, or it has to wait for a message from another process. Or it has to wait for an input. That means this process has to be blocked and has to be taken from the execution state, the running state, and put into one of the queues, the event queues. So a process had requested a system call that is blocking, for example, an IO. Or that process has, asked to be suspended, meaning put in sleep. It wants to wake up at a certain time. These like backup processes. They wake up at certain times. They do its job, and then after that, they get put to sleep, and they want to do it like in some other time. Or a process has initiated a signal, and that signal could be an error, and that error would call for the termination of the process. So a process is running, it encountered an error like division by zero, or by like caused the parity error. So at that time it doesn't make sense to execute the process. So the process has to be terminated. It has to be killed. So another process would be picked and selected from the queue to run. An example of process that would encounter errors could be like a process is running. It has a bad address, a bad pointer. Could be a programming error, and therefore the process has to be stopped. Or another interesting thing here is that a process would be running, and all of a sudden you hit the Control-Alt-Delete. So that's an interrupt, and it indicates that a higher priority a process has to run like the task manager in this instance. So this is a good way to run a different process. Okay, so these are sort of like reasons that would tell us it doesn't make sense now. Based on an interrupt now, whether it's software or hardware interrupt, doesn't make sense to go back and run the same process that encountered the interrupt. We have to go and run some other process. So in all of these situations, we do a context switch. Okay, that means the operational state of the process has to change from running something else, and depending on the cause of interruption, it can go from running to ready, running to blocked, and things of that sort. So okay, it's important. This is an important slide, and it's important information. So let's move to the next slide. And next slide, what really happens when we do a context switching? What are the mechanics of a context switch? What we do as follows. See, what happens is that a process is running. So what we need to do first is to copy its contents. Okay, remember we have the contents of the CPU registers that were pushed in the stack because an interrupt happened, a software interrupt, or a hardware interrupt. So the first thing that we do, this content has to be copied from the stack and put somewhere else. Well, it has to be saved in the PCB. It has to be, because we said remember, in the PCB is the data structure, and actually it's a bucket, it's a container of lots of information, and so part of this information is the state of the system when the process got interrupted. So the general purpose registers, the stack pointer, the program counter, and PSW. So we need all of this stuff, because at some point we have to come back and execute that process again, and it is important to execute it in the same operational state or in the same running state that was interrupted in. So these registers, we have to save it in the PCB. So this is the first thing. The second thing, an interesting one, is to change the status. And we said, like, each process in its PCB has a status. It could be running, it could be really blocked, or block suspend, ready suspend, one of these things. So it's the status has to be running. And you think about it is like this: the process was running and it did something, or something happened to it. Okay, so the process either requested something that caused an interrupt, so it initiated a system call that caused a software interrupt, and that software interrupt changed its state, and it has to be a blocking system call. Okay, so it's a state change from running to something else. So if it initiated like wants like to read a disk block, so the state would have to change from running to waiting. If it was running and then it changes a system call that is blocking, like wants to make a message or waiting for input again, and its running state will change from running to blocking. But if it was running and all of a sudden a timer interrupt, and that timer interrupt is the timeout interrupt that says, well, this is it, your CPU quantum has finished, then its state will change from running to ready. Okay, so we have to really study what really happened when the process was running. Was it a timer that came and said, okay, it's over for you, it's timeout, or was it the process itself that did something, and we have to change its state. A process could be running and all of a sudden it's finished, so its state would be terminated. A process could be also running and all of a sudden encountered an error, so it has to be taken away, so it will be terminated. Okay, so there are different ways that okay, so what happens? A process that was running, back to here, process that was running and then encountered something that caused its a change to it's a state to change from running to something else. Or there are, as talked about, there are different reasons for that. Now after that, a new process has to run, right? So a new process has to be selected to run, and the CPU scheduler will determine what the process to run. So we select a new process and we change its running state. So a running state of this process has to change from what to what? From ready to running, right? Because it started running, and we have to select it from the ready queue. Okay, this is here the ready state. If I can write it right, I can't, but it starts to change to running. Okay. Okay. So it has to change from ready to running, and that data state. This is the first thing we do to change state, but the process is not running yet. So what we have to do to let the process run, we have to call the dispatcher, and the dispatcher has to load its CPU registers that are found in this PCB into, okay, this is important to see, into the CPU registers, okay, the actual CPU register. So there are all saved CPU registers that were saved at the time of the start of the at the time of interruption. So we save it in the PCB. Now when we resume the process, we have to read these CPU registers from the PCB and then load it, copy it into the CPU register. And the last thing, okay, the last thing that will be copied into the CPU register will be the program counter. So we copy the program counter into the CPU register. Now the process start to become alive and to start to be running again. Okay, it's important to see that, right? Right. Just some notes here. Okay. Context switch is pure overhead. Okay. This is switching all, executing all these steps do not does not come free. We have to pay for it. So this is processing overhead that is wasting. And then you can nowadays some CPU architecture, modern CPU architecture and design, they have what's called hardware assisted instruction to do that. So copying the register will be done rather than in multiple instructions. Instructions will be done in one instruction. So copying the register from the stack into the PCB is automatic. Also loading the register from the PCB into the actual CPU register would be also automatic in one instruction. Step number 3, let me change the color here. Change number 3 is actually determining the order what the process run. That is the scheduler. And number 4 would be the dispatcher, the loading of CPU register, the loading of information or data that is stored in the PCB registers, PCB, the PCB block into the CPU register. This is pure dispatching. Okay. Let's look next at sort of like how we do context switching. Okay. So we have here in this, we have process 0 and a process 1, and we want to switch between these two. So we do it sort of like multi-programming between. Okay, this is the last part. We'll talk about processes here, process creation. This can be pretty involved, but the simple idea is as follows. We have process, parent process creates another process, and that new process, the child process we call it, can have another children. So we have in a way what we call the family tree. Okay, but so it looks like this in the following slide. So we've got here a tree of processes that this is for Solaris, another Unix-like operating system. You get the scheduler, which is actually, this is the parent process with process ID 0. It will create the init process, which process ID 1. These are from Solaris. These are true process IDs, and then from that we can create init ID, that would, responsible for like telnet daemons and C shell and so on and so forth. So a process could create another process and so on and so forth. So this is a view of a process family tree. Okay, let's go back to talk about what happens when a process creates another process. There is some sharing of resources between the parent and the children. So we said, like, for a process, it would have a code segment, a data segment, and a stack segment. And depending on the way that we create a child, we can share all of these with the process. Or the child process can share all of these with the parent process, or it can share only the stack segment. Meaning it can share the data segment and the code segment, and the stack segment has to be always different. Okay, so we could have parent children share all resources, okay, except for the stack segment, of course. The children share a subset of the parent process resources. So when we make that creation call or creation system call, we could share only the code segment, and the data segment would be different. Of course, the stack segment has to be always different because it reflects the running state of the process. Or nothing shared. The code segment is different, data segment is different, as well as the data segment. So in the execution, what happens when we fork or when we create another child, both are running. The parent process is running, and the child process is running. So what happens as a good way to do that, if we want to terminate a child, okay, we do not kill the parent. So a way to do that, the child terminates, waits for the parent, the child terminates, and then the parent would terminate. So the parent has to wait for the children to terminate before the parent dies or terminates. There are two different Unix system calls. Remember, these are system calls. Okay, and typically they are blocking system calls, by the way. So we've got the fork and the exec. The difference is that when you do fork, you've got a child process is running, and then when you do exec, you get also, it is similar to fork, but what happens, it replaces the process memory space with a new program. Okay, this is a bit complicated, but I think this is enough. Okay, so a fork, you have with a fork, you've got the parent have a code segment, data segment, and stack. Okay, and the child would have similar code segment, data segment, and stack segment. With exec, that code segment, data segment, and stack segment of the parent is gone. Okay, so it is replaced by the it is replaced by the child one. So you don't have two code segment, two data segment, and stack. So you just have one. It's involved, but this is basically that. But it is okay. Let what happens here. Okay, how we in the assignment, I plan to give you something similar to this. So here's a fork. Okay, you've got the parent and the process running, and then now there is a child process would run. Of course, what when we do fork, we need to have the child sort of like doing different code than the parent process. So we have here a fork. Now we have the original parent is running. Then we have also a child that's running. But to have each one execute a different leg of code, what we do, if that ID, this is a process ID, returns a 0, then it's for the child process. Otherwise, if it is 1, that would be for the parent process. So here we can put any code we want. Okay. So this code will be different. This is only child code, and this is only the parent code that would execute. So if this is the child process, then it would execute something like ls, okay, and then it's doing this by exec. Okay, exec is another fork, but it's doing this one. It's like a system call doing this, and then you've got the parent process, and that parent process would wait for the child to finish executing, and then everybody, the system will exit normally. So here's a fork, okay, that is done by, then you have, here you start with here actually. You do a fork, and this is the parent leg, and this is the child code, and the child does exec. Okay, it's another fork, but we don't have another process. It just overwrites the memory space allocated for that process, and then at some point that would exit here, right? Well, actually, no, it'll exit here, and then it'll hit this one, exit, and once it exits, it'll go for it's sort of like a signal that would will be received by the parent as it was doing a wait, and then both at this time will exit. So the parent and the child are all dead, all terminated, and they're terminated cleanly. This gets more involved in the way that how exec is different than fork. Okay, but exec is basically a fork, but it overwrites the code segment, data segment of the parent. So you get only one process running.